Okay, we're now ready to define general rational exponents, and we have a to the m over n. This definition follows naturally from what we had before. So recall that we had a to the n equals a times a times a times a n times. If n is an integer and n is positive, and of course a to the 0 is 1, and then a to the minus n is 1 over a to the n. And this gives us a to the n for every integer. And then we defined a to the 1 over n is that unique number such that b to the n equals a, and if n is even, then we must have a greater than or equal to 0 for this to work. And of course, if n is odd, then a can also be negative. And now remember, our rule of exponents says that a to the x to the y is equal to a to the x times y. And so if I want to define a to the power of a rational number, say m over n, where m and n are integers, then I must have, since m over n is m times 1 over n, that must be equal to a to the 1 over n to the power of m, or a to the m to the 1 over n. And of course we also need a to be greater than or equal to 0 if the n is even, in order for this to work. And so that gives us basically our definition, and that's exactly how we define a to the m over n. So we have a to the m over n is the nth root of a to the 1 over n to the power of m, or equivalently the nth root of a to the m. And if n is even, then because of this, we must have a greater than or equal to 0. And now the laws of exponents work, so you can check them out. They're not terribly difficult to prove. Most of the proofs would follow from proofs of the previous laws. And we have the following laws of exponents, which hold for general a to the x, where x is a rational number, given that a is the appropriate a, that it's greater than or equal to 0 if a to the n, if n1 or n2 are even here. And so let's assume that x is a rational number m1 over n1, and y is a rational number m2 over n2, and we can assume that the n's are greater than 0 here, because if this is a negative number, we can assume that the minus goes with the numerator. So we have a to the x times a to the y is a to the sum of the exponents. And if I divide powers of a, I subtract the exponents. If I take a power of a and raise it to a new power, I multiply the exponents. And if I multiply a by b and raise all of that to the power of x, then I distribute the exponents. We have one last rule, which is very similar to the previous one. A over b to the x, I can distribute the exponents, and that's a to the x over b to the x, assuming b is not 0, because we're not allowed to divide by 0. And then in Calculus 2, you go on to define a to the x for any real number x, either by using limits or as an inverse function for logarithms. And the same laws will hold. So when you're calculating with exponents, these are the laws you will always use. So let's look at a few examples where you might calculate with these. And actually, let's add one more example here. 2 to the x squared plus 1 all to the power of 1 over x. You may want to pause the video for a little while and try these. We're going to try to simplify them and then have a look at the solutions. So for A, we have 2 times x to the 1 over 4 over y to the 1 over 5, all raised to the power of 5, times y squared over x. And now, according to one of our rules here, rule number 5, we can distribute this power. We get 2 to the 5 times x to the 1 over 4 to the power of 5. So this is all of this to the power of 5, distributing over the numerator and denominator, but also using rule number 1. And then we have y to the 1 over 5 to the power of 5 times y squared over x. And remember, y to the 1 over 5 to the power of 5 is actually equal to y, because 5 is an odd power. And so this is 2 to the 5. This is x to the something, a power of x, all raised to a new power, so I multiply the exponents there. And I can amalgamate the two fractions and multiply by y squared. And I get y times x here. Now I get a little bit of cancellation by subtracting powers. So I have y squared over y is y to the 1. And here I have x to the 5 over 4, so I'm going to break it up as x to the 1 plus 1 over 4. And I've cancelled a y. And now I'm going to break this thing up. It's 2 to the 5 times x to the 1 over 4 times y over x. Now this x will cancel. And that's 2 to the 5 times x to the 1 over 4, the fourth root of x, times y. So that's certainly a simplification. And now let's try B. Sometimes people find these nesting square root signs a little confusing, so that's why I've included this example here. And the first thing I'm going to do is convert this thing to a power so that I can see clearly what's going on. So this is x to the 3 times x to the 1/2. And that's the square root of x to the 3 plus 1/2. And that's the square root of x to the 6 over 2 plus 1/2. And that's the square root of x to the 7 over 2. Now, I'm going to write that square root as a power of 1/2. And now I can see what to do using one of the laws here, a to the x to the y is a to the x times y. I just multiply those powers. So that's x to the 7 over 4. And that's it. I've written it as a single power of x, and that's certainly a little simpler than what I was given. Now I've included the third one. Later, when we generalize powers to all real numbers, we'll be able to take 2 to the power of a function of x, and then again to the power of another function of x. But here, because we've only defined powers for rational numbers, we can assume that these are rational numbers. And the point here is that 2 to the x squared plus 1 all raised to the power of 1 over x is 2 to the x squared plus 1 over x. I'm multiplying the powers here. And that's about as simple as it gets for the moment. The reason I included that is because sometimes people get a little confused when we put x's into the exponents. And of course this happens quite a lot in calculus because these are functions that you're going to examine and try to figure out what's happening to them.